The best place to start with a new idea is a definition. The Laplace transform is defined as follows. The symbol here, this curly L, means the Laplace transform, or take the Laplace transform. We typically use curly brackets around that, and then what we have here is the original time-dependent function. And what we get back, all this together, gives us the output, which is the transformed function capital F of S. Notice the t's are gone, and so what we started with was a function of time. What we end up with after the transform is over is a function of this new variable s. How do we do that transformation? Well, what we do is we simply take that function f of t and we put it into this slot in this integral form. So we're always going to integrate from 0 towards infinity of e to the minus st times whatever the function is that we're transforming, and we'll do the integral with respect to time. Now, of course, this is a classic improper integral, and by improper we mean that the limits here are not a nice finite value, but they're infinitely large, and so we have to work around that. And the way we do that, of course, is to say we integrate up to a finite value b, compute the value of the integral, which will be finite. And then we ask, well, what happens as b gets larger and larger and larger? And then we'll have the value of the integral out towards an infinite interval. So that's the definition. Our next question is, what kind of functions might we want to work with? Having seen solutions of differential equations so far, what kinds of functions have we seen? Well, we've seen a lot of e to the at. E to some constant has shown up quite a lot. We've also seen sine of bt, we've seen cos of bt's, we've seen mixtures of these, we've seen t e to the at, we've seen e to the at sine bt's, we've seen e to the at's cos bt's, and think back if you can right now to what kinds of differential equations gave rise to this, or what forms. Think unique solutions to the characteristic equation, complex solutions, repeated roots, and we actually had on occasion simply constant functions and t squareds, so polynomials as well. So that's a good starting place for asking what kinds of functions should we know the transforms of, because we know these are going to show up in our study of differential equations. Let's start with the simplest example of all, f of t equals 1. So if we're trying to transform the function f of t equals 1, technically it does not have a t in it, but it's still a function of time the way we've written it here. Using our new notation, what we're looking for is capital F of s, based on the transform of little f of t, curly L of the function 1 is what we're looking for here. And that, by definition, is the integral from 0 to infinity of e to the minus st times 1 dt. So this 1 is just being put into this slot in the integral form. And that's what we mean by the transform of the function 1. Now we simply have to evaluate that integral, which is well within our abilities. What we're going to do, of course, because s is not t, is treat s as a constant during the integration process. So what that leaves us with, let's do the first step first, which is to rewrite this as a proper integral from 0 to b, but with a limit afterwards that'll let the upper boundary go to infinity. We can ignore the 1, it's just a multiplier that disappears or can be invisible. Our next step is to actually evaluate the integral. We copy the limit down, and then we ask, well, what's the integral of e to a constant times t? Well, the integral is e to the same constant t divided by the constant, minus s here. And that'll be between b and 0. And that will give us the limit as b approaches infinity of negative 1 over s e to the minus s times b minus e to the 0. Now, to evaluate the limit, which is what we can do now, we're going to use larger and larger values of b. However, there's a little caveat. Here we're going to have s greater than 0, because if s was less than 0, we'd end up with a positive exponent here, and this function would go off to infinity. However, so long as s is positive, what we're going to get is this term here is going to approach 0. We have a negative exponential. It decays to 0 as b approaches infinity. And so we end up simply with negative 1 over s times negative e to the 0, which is negative 1, or 1 over s. And so how would we write that in short form? The Laplace transform of the constant function 1 is 1 over s. This is our function with t's in it, theoretically, and this is our function with s's. So not too exciting yet, but we're building some groundwork here. We'll see the transform of other functions as well, and see the kinds of patterns we get once we've completed those transforms.